Let's dive into the world of image classification using a simple example. Imagine we're working with the famous MNIST dataset, which contains handwritten digits from 0 to 9. Each MNIST image is a 28 by 28 grid of pixels, creating a total of 784 pixels. To feed these images into a neural network, we first vectorize them. This means we turn the 28 by 28 grid into a single long vector of 784 numbers. For a clearer visualization, let's apply this to a 4 by 4 image. Our neural network is designed to classify these digits into 10 classes, one for each digit. So we have 10 output neurons in the network. Each output neuron is connected to all the input pixels. The outputs of these 10 neurons go through a special layer called Softmax. This layer transforms the raw scores into probabilities. Softmax works its magic by applying exponential function to the raw scores of each output neuron and then normalizing the vector. Consider the raw scores of each output neuron for the input image of digit 8. The Softmax layer applies the exponential function to each of these scores, followed by normalizing the vector by dividing it by the sum of the vector. This process yields the probability distribution. Likewise, for other digits, the neural network generates output probabilities indicating its predictions for each digit. Training this network becomes more stable when employing log softmax instead of softmax. During training, we input the network with training images accompanied by their corresponding labels, represented as one-hot vectors, shown here for digit 2. Negative log likelihood, also referred to as cross-entropy loss, serves to quantify the difference between the predicted probability distribution and the true probability distribution denoted by the one-hot vector. The generalized backpropagation algorithm is then employed to iteratively update the model parameters, ensuring that the output closely aligns with the true probability distribution.